Part 2 of problem 2 asks us to demonstrate that given n independent variables, x1 through xn, all drawn from this distribution which takes the value p with probability p and the value 1 minus p with the remaining probability 1 minus p, the probability of this event written right here, that the log of the nth root of the product of these variables over p to the p times 1 minus p to the 1 minus p, has absolute value greater than some value epsilon, approaches 0 as n gets large. Now I realize that's a mouthful, that's a very complicated expression to keep track of, but it's essentially the same expression that's used in the law of large numbers. What's going on here is that in the law of large numbers we say that the average of a large number of independent variables drawn from the same distribution should almost certainly be equal to the mean value of that distribution, or I should say should be very close to the mean value of that distribution, the expected value of that distribution. And the business with epsilon is just a way of formalizing this business, and the limit and the epsilon are both ways of formalizing this business of being almost certainly very close to the mean. The average of a large number of independent variables drawn from the same distribution is almost certainly very close to the mean of that distribution. And what's going on here is the same thing. We just have to use some algebra to rewrite it in such a form that it is, in fact, exactly an instance of the law of large numbers. So let's do that algebra. So this expression in the middle here, I'm going to rewrite. Since we have a log of a ratio, I can rewrite this into a difference of logs. It's the log of the nth root of x1, x2, etc. through xn, minus the log of p to the p, 1 minus p to the 1 minus p. On the left, this again I can rewrite. An nth root on the inside of a log turns into a division by n on the outside, and then the multiplication on the inside turns into addition on the outside. So we have log 2 of x1 plus log 2 of x2, etc., all the way through log 2 of xn divided by n. So this whole thing is turned into an average of n different values, the average of the logs of x1 through xn. On the right, again using basic algebra for logs, this turns into p log p plus 1 minus p log 1 minus p, which you may note is the same as the expected value of the log of a variable drawn from this distribution, which takes value p with probability p and the value 1 minus p with probability 1 minus p. So now we see that the expression that we're looking at is just the difference between the average of n values drawn from a particular distribution and the mean of that distribution. Here the distribution is the one which takes the value log p with probability p and log 1 minus p with probability 1 minus p. And the law of large numbers tells us very directly that for this distribution, just like for any other distribution, the probability that this difference between the average of n independently drawn values and the mean of the distribution having a magnitude greater than some particular value epsilon goes to 0 in the limit as n goes to infinity. So the answer to this problem is just to observe that after some algebraic rewritings, the desired statement to be proven is just an instance of the law of large numbers.